So Ran is missing.
Ran will be late, so we can start.
Okay. There is an important aspect which I forgot. Does he have the flower? In a sense, we bought it, but I don't know if it's
What, sorry?
the flower.
No.
No, it's important. Can you send a message to him?
Bring the flower?
Yeah, because I don't know if it's in the bag that he told me to organize things with the flower, and I forgot if I put the flower in.
The flower, Ran has to bring it.
Yeah, has to.
Okay,
Yeah.
I'll
Just
make
okay.
sure he does that.
Sorry, guys. It's suddenly. It's not recorded. This, no. Oh, okay. Okay, we'll worry later. So let's start. The first thing is I just wanted to comment a bit on the exercise some of you might want to do this afternoon, which is the fourth exercise. A comment in the sense I want to show you what it should look like, the output. And then a little bit on the simulation yesterday because there were some issues. So just to, everybody's present, I'll say it again, maybe you've heard me already. But so if you do the fourth exercise, which actually I haven't written what you should do. So let me just give you the details. Some of you have started, but remember that there is a circular arena of 1 meter diameter. And then you have 12 or 11 trajectories. And this, I think they have precisely these names. And these are laboratory rats that move searching for food in this semi-dark environment, which is confined, precisely of this shape. And your task is to plot the mean square displacement with a technique which is time window averaging that I told you yesterday. And so this time here is indeed the time window that you are picking to then determine the mean square displacement value. So you take, let's say, whatever here is 25 milliseconds, and then you go with this time window of 1 over the entire trajectory, you get 1 point. And it's, of course, there are 11 trajectories, so you're going to have 11 separate points. Now, the time scale is not exactly, we were just checking, I forgot your name? Near. We were just checking with Near if it was exactly regular. It's not exactly regular, but take it as such. 25 milliseconds, I think it's. So one unit of time of that data set is 25 milliseconds. So delta t measurement, I think it's 25 milliseconds. And now, what is the actual data that you have? So you have x and y coordinates for each trajectory, but they're not in units of meters or whatever, centimeters. They are actually numbers, integers, because there is a grid underneath here. And let me etc. So the experiment was set up such there was a grid painted, whatever, on the surface, on the bottom surface, and the animal had this LED, and so the camera was looking where it was, and then I think manually what they did is that, I hope not manually really, but there were lots of data points, but what they did is that where the animal, they saw the animal, there was the grid, they saw the light, and then they assign a number there. So it's a discrete coordinate system that you're going to see there. Now, since you have this information about 1 meter, and here you will see when you plot this data, what you should do, you just take one trajectory, you take all the data, you plot x, y, so you just see the entire trajectory, which fills the entire space, so a big blue blob. And then you will see, essentially I will define for you the contour. And then you will just look at the minimum coordinates that you have, the maximum here, and so you just know it 1 meter, so you're going to know what is the distance between the center of this and the center of that. And why do you need that information? Well, if you want to put meter squared here, you need that. If you want to put just those numbers, then of course you don't need that. I mean, you're going to set the same plot, but without the right units. I mean, without units.
Can you repeat that? I didn't understand.
So from here?
Yeah, I understand the grid.
Okay.
But just why is it important if you use square or not?
If you
the last sentence.
Oh, so what I mean, this is to plot this with the right unit. So you need to know what is the fundamental length scale.
So the length scale is a
one unit here.
1 unit.
So 1 unit is that unit, whatever that is, you find out by calculating here. And so then, you know, whatever 1 unit there is, then you're going to know what that 1 unit. And
the data is in discrete space?
yeah, the data has, you know, it's integers here, whatever. I mean, that's, I don't know. I think the 0, 0 is down here. So you're going to have 200, 300, and so on. No?
Discrete.
Yeah, so this is indeed discrete. Now, just keep in mind that this, I mean, if you do the same here, you try to measure the distance. I mean, you try to take the extreme data point here and the extreme data point here for the trajectory. It might not be the distance in numbers. It might not be exactly the same as this one, because this is where the animal has been. So it's not the actual boundary, but just take an average between the y and the x. So that gives you the fundamental unit. Follow? Clear, no? So do you want me to write in the PDF exercise for all of this, or do you remember? Better to write. Okay, I'll write it later. So this is all for the exercise if you want to do it. Now, I know some of you will want to finish the other one, so I'll be there, so whichever you want to try to do.
And you will give us the data set in
Oh, sorry, the data set, it's CSV files.
Under LG files, Luca Giuggio.
Good. So, any question on that exercise? So notice the time scale here. So, you know, worry about plotting up to this kind of time scale. As you start going farther out, you remember the time window averaging is giving you more errors. So you don't know anymore if these oscillations are really real or it's just a noise. I mean, I can upload this figure. I mean, I just take an image and just, you know, so that people can check.
You can upload the whole...
Well, this is a paper I'm writing. Let me just upload the image.
So. If you do the analysis quick enough, you can publish before him.
Oh, that's true, actually. So, okay, so we are done with this. Now, a comment I wanted to make on the simulation, what is it? So we are having a little bit of few difficulties on the simulation, and thanks to Orr, we are all safe. Thank you, Orr, because he found a trick to avoid, or at least to get and see this damp oscillation, is that, you know, we have our square for, this is for the correlated random walk in 2D, and we wanted to plot out of the many trajectories the mean square displacement versus time. No? And so the correct simulation, the one which is going to give you this very smooth, well, the theoretically very smooth curve with the correct properties, is that, so what is a boundary condition? Is that if you have a component of your jump, which will be a vector, you go from here to, let's say, you would have to reach there suddenly because you close the boundary, then what happens is that you decompose this one always a component like this and a component like this. And then this is a reflection which for the y component. So if you would have to do the correct simulation, then you throw a random number with an angle and a distance, and then what you do, you reflect that one. No? So then you will get a reflection which are optical reflection. So this, no, I know. So I'm just saying what the actual simulation, the correct simulation, so this angle is equal to that. So if you precisely do that, then you get this fantastic smooth curve with many simulation. And what you saw, I was telling you yesterday. Now, I wanted to find a shortcut for you, and I told you the one which didn't work quite well. So what R has found out that if you actually, when you essentially, this is going to work particularly when you have high correlation, because you can imagine that if you go, and then what it does, you just backtrack with a pi angle. So in other words, even if you are doing like this, you backtrack. So it turns out that it's sufficient enough to give you those features. So if you do that, it's much easier rather than trying to, because that becomes quite complicated when you start being close to the corner if you have to take into account all of this. So just do what R has done, and most of you have done it already. So is it clear? Good. First passage. Now, lectures of today, it's about first passage times. And I actually, so this was the thing, the B? No. Oh, no, Control B.
Just B.
Just B?
But you have to be in the PowerPoint.
Oh, sorry, in the PowerPoint. So, I mean, as a slideshow.
Yeah.
Okay, so this is the lecture. Okay. Who has heard about this name, first passage times? Just 3 or 4 of you. So let me say what it is, therefore. So the idea of the first passage processes, if you want, these are those processes for which essentially you have a threshold phenomena. So you start in a certain initial condition, and then as you reach, that variable reaches a certain value, then something happens. So it's enough that that variable reaches that value. As soon as it reaches, then you have something catastrophic or something very beautiful happen. So what is important about the statistics of that variable is when it reaches that specific value for the first time. So that's why it's a threshold thing. So now, so far what we are looking at, we're looking at mean square displacement. There is no threshold there. So we are plotting versus time what all these possible values might be. So if I think in terms of movement, if I start here, and then I consider the value of possible trajectories, and then what I compute at a given time, then I check, oh, where are all these data points? And then I make an average. So if you really want to think about the threshold is the time. So you pick a time, and in some sense, but so there is no really a threshold here, a special threshold. So you decide the time, and then all this trajectory will give you this value, which this mean value in this case was the mean square displacement value. So this is an initial value problem here. You start at some point, and then you look what happens after some time. On the other hand, first passage times, in the way we are going to use that, this is a boundary value problem. You have an initial position, and then you start to ask the question, when do I reach my target? Now notice, here there was no target here. Wherever you go, it doesn't matter. You just compute what this mean property of this trajectory is. Now suddenly you have the same, always an initial condition, but now it's a boundary value because you ask about a specific point. Is it clear the difference?
Is it a specific point or a specific distance?
It could be also the distance. Yeah, I'm just starting to explain. So of course, I could do this. Then I have a distance.
You start from the middle?
You don't have to, but of course, a lot of times when you do this kind of calculation, you want to start from
one point and you want to see that when does it reach the displacement, or you
No, you start, well, both. You'll see, we'll talk about both. So in this case, since Or was asking me, oh, I can ask the question, how much time it takes to reach for the first time. Notice I'm always going to say the first time, and if I don't, remind me. So the first time to reach this point, or I can ask the question, how much time does it take for the first time to reach for the first time any of the point on the boundary? So the set of targets could be one or could be many. Now in general, one is a simpler problem than many. And why is it a simpler problem than many? Because if I'm looking for the time it takes for me to reach either of these points, the trajectory are quite complicated. The reason being because if I'm going to make this discrete, you know, these are the targets, etc., etc. And then I ask the question, how much time does it take to reach either of these? Then when I calculate, I do some stochastic simulation, and I calculate how much does it take to reach this one, and then I take how much does it take to reach this one and this one and this one, I always have to calculate, assuming all the trajectory that have not reached the others before reaching that one. Now you have to think what I just said. It's not easy. So if I'm trying to compute the first passage time to any of these points, then the trajectory that is going to give me the right statistics are those that do that. They don't touch any of these, and they go there. Because if I have one which does that, then contributes to the first passage to this point. So trajectory, so you partition the trajectory in a quite complicated fashion. That's why a multi-target situation is much more complicated than a single target. Now it's not, this is not immediate to understand, but.
Why does it matter which point?
No, this, I mean, in the overall computation doesn't matter because you are taking what is the average time to reach either of those. But I'm just saying, if you start doing simulations, the way you would do it, the actual trajectories would be, I do all the simulation, and I take, you know, you check how much time it takes for me to go from here to there. If you want to separate the trajectory, really, of course, you know, you would do in a more intelligent way, the actual simulation. But then you would say, OK, then I compute all those. They reach here before reaching neither of the others. Then I add the one that reached here without reaching neither of the other one. Because this is a first passage. So as soon as you reach here, the process is terminated. So it's finished. And then you account for those times as you build this average time. So maybe if I give you two examples, when you have one target, I mean one source, so which is a point, and then two targets. So imagine that I take into account all my trajectory that do this, and then eventually they do this, but I cannot, if I want to compute the time to either of the two, then this trajectory, if it does this and then this, it's not correct in the sense I should not compute it. I should exclude those. Because this trajectory, if they just hit this target, this corresponds to the time it takes to go to this one. And then you do the average between the two.
It's distance, not the It's distance, not the target.
No. This is, remember, I'm computing time. I mean, of course, it matters what the distance is, but I'm computing the mean time, the mean first passage time.
To add the distance, it doesn't matter.
Yeah, okay, correct. Now, if you do the actual simulation in an intelligent way, you would not partition the actual processing the way I told you. In this case, because you have circular symmetry. In this case, you do. In this case, you would have to partition in that way. So in this case, you definitely have to partition that way. You start here, you compute all time it takes there, and then if you want to partition, then what are the trajectories that contribute to create a mean time to get there, are all those which have not reached there. Yeah.
What is the biological meaning of such a computation? I mean, the animal is not going back to the emergence point, so why?
No, yeah, so the biological depends on the problem at hand. So this is really a physical quantity, which is telling you how much time on average does it take for me to go from one point to another point, or from one point to either of these points. Now, the typical biological meaning, I would say these are food targets. Suppose they don't move. If they start moving, it's even more complicated. Suppose they don't move. So you want to understand, forage is efficiency. So you have a set of targets, and then you ask how much time it takes on average to pick either of those, so that I know how much time.
For such an animal, it doesn't matter if it moves from the first to the second, but you find that you want it to go back to its burrow and then.
Yeah, because the point is that you're right. But I would say there is even more complexity there, because as you reach your food target, or let's say sometimes you can call it a patch, then your efficiency in actually grabbing the food maybe is very low. So then you have other things which are called return times, no? So then, you miss it, but you have been there. And so then you have to compute the return time. So these things can be quite complicated. So if you want to have a rough estimate, if you have a set of targets and you want to know what is the mean time I need to get there, so I have a set of patches, and then you want to know, given a density, there is an average distance between them and from the target, then you can try to do this kind of calculation and say, oh, on average it takes such and such amount of time. Yes?
I didn't understand why the single point case is less complicated than the multi-point case. Because it seems that in the multi-point case you can just integrate over all trajectories which reach the boundary.
Yeah,
you don't have to exclude anything.
Okay, let's say maybe computational is more complicated. You're thinking intuitively. Intuitive is the same thing, but computationally you have to separate these kind of trajectories. Now there are clever way of not worrying too much, and when you have a circular target, for example, you don't worry. You just do the simulation as soon as you reach a distance r. Boom! I finish one data point and so on. So. Intuitively, it's the same concept. It's just either of the two. But if you want to calculate the probability to get here before getting there, which are called splitting probabilities, or if you have two or more targets, then you would see it's much more complicated, because to avoid counting these trajectories.
Are you saying when there is only a single point in space that you want to account for?
Say again, when there is?
When there is only a single point in space that you want to account for, so that's simpler than
many. Yeah. Because you have, the actual computation goes like, I compute the probability of reaching this, not the others, then of reaching this, not the others, of reaching this other one, not the others, and then you do the average over that. Okay. All clear? So this is, we're just explaining you the theory, the intuition rather than the theory behind this. So, no, this is something that I'm working actively on. And I'm sure that you're going to ask me, what about the correlated random walk and so on? I don't know yet the answer, because I'm really working at the moment. Because you can start asking the question, if I start here, and then I have my distance of target, and then you can ask the question, how much time it takes for a random walker or for a correlated random walker? Fair question. I don't know yet the answer. So, of course, it's inversely proportional to t if you want, the capital T we talked about, and and there are these nasty infinite series that they come about, and I'm going to explain you why. Without showing actually the result. But if you want, I can show you the one in the random walker. But intuitively, what you would expect to be this average first passage time to get from a center to a set of targets which are in in this symmetric geometry.
Related to capital.
No, okay, yeah, that's true. Let's talk about the random walker, which is the one I'm going to tell you that I know exactly. So, okay, what are the parameters of the random walker? There is a diffusion constant. And if it's unbounded domain, that's it. No? So, and if you have a radius r, what would you expect that to be? Yeah, so, well, an area divided by diffusion constant, essentially. I mean, not putting the coefficient here. Huh?
You don't have to square also the diffusion constant, because that's a linear property, no?
No, because this is a distance squared divided by time, so that gives the right property. So it's r squared by d. So area, so in other words, you always have to get something which is an area divided by the diffusion constant. Now there are people, I'm going to tell, this is in relation to segmentation. I'm not going to tell you anything about this. I'm also actually involved in thinking about using this kind of technique for segmentation. But if you think about the trajectory, and now, I just have the trajectories. Let's suppose an unbounded space, an individual which doesn't have a home range, and then this point, imagine if it represents this point. Then I draw a circle around here of a given radius. And then I can ask, given that the dependence is, well, the radius I know because I'm going to put that radius divided by the diffusion constant. If I want to know what the diffusion constant is from that trajectory, do you see what I would do? You already see, no? What would I do? To exploit the fact that I know precisely those coefficients, and I know the area, I know the process it takes to go from here to any of these points. So in other words, I know the time it takes to go to reach this radius. Yeah, but what would I do on the trajectory? Okay, but that would be 1 point, no? Okay. So you slide, another sliding here. So you slide this object, which is your radius here, onto the trajectory. So now you build the statistics. Remember, this is a mean, So then you're going to get your mean for a given r. You choose the r.
Can you repeat this?
Okay. So you understood now what happens here. If you have an animal which starts at the center, and you suppose you have a set of targets here, which means as soon as you reach one of those, then you compute the time it takes. And there could be many different ways to get there. So there is a mean, because there are different trajectories that could reach.
This is time?
This is a mean time. So there is a tau here. So you would do a simulation. You would just put all these possible trajectories, and you average over all of them, and you're going to get a mean time to get to a distance r from your starting position. And I'm telling you, theoretically, it's the area divided by d. So, I mean, without telling you the exact coefficient. So you may think, OK, so if I do this, if you do the simulation to compute the diffusion constant, since you know the area because you input the area, you choose the radius you want, no? Then you do that, and you're going to get the mean time. And since you know the area, you're going to know the diffusion constant. So a characteristics of the animal movement. Now again, remember, so there is always a simulation, there are the data now. Now we go to the data point. Now this is the trajectory. And again, assuming that the animal moves as a random walker throughout its entire observation, then I'm just going to represent this through my data set. So I put a radius here. I choose a radius. And then I say how much time it takes for me to get to this distance. And then, since you have a trajectory, you want to generate synthetically many trajectories, as you did in a simulation. So you put this radius here, over here, over here, over here. And then, in some cases, I mean, there will be no heat in the sense. But if you put the bigger radius, then, okay, whatever. I should put like this, sorry. Huh? Now suddenly you have a hit.
So your radius is constant, but because you have varying step length, sometimes you will hit, sometimes you will not hit.
Correct. The point is that you study the process function of the radius, because that's the one you change. Yes?
If I have want to calculate, I have a random movement, but the boundary is any shape.
The boundary of what now?
The boundary that I'm trying to reach, the first time to reach a certain boundary. Is it proportional to the area?
Yeah, it's still proportional to the area. If you're not interested in, I mean, there are, yeah, you can show that it's still proportional to the area.
No matter what the shape is?
Yeah, I mean, of course, it does depend on the shape, because, you know, if I have such a boundary, then there is an aspect of what is it that you are approximating. So you can compute this area, and then this is, so there is some effect. Now, if you ask me what is the effect on the coefficient here, I don't know. If you start changing quite dramatically the shape.
But it's proportional to this.
Yeah, but this is, you know, things, I mean, dimensional analysis is going to tell you that this is going to be, that's your time, no? Now remember, if you put really a complicated shape, then the coefficient here could be dramatically different than, let's say, 1. So then what you're going to, then if you want to find the diffusion constant, you know this and you know this, but then the coefficient here is so wildly different than 1, let's say, so then your computational D doesn't make much sense, no? So it's not the reality.
Okay.
Now, if you do comparative studies, then you don't care, because if you have that shape for the same individual, or maybe a different species, but the same shape, then you don't care about this coefficient, because it's going to be the same.
But my question is this. If I have two shapes, random walker, two shapes of the same area, but totally different shapes, they will have the same first passage time?
No, because the coefficient here is going to change. They're not going to add this. There is some dependence. It's not an important dependence up to a level, I mean, up to a point. No? Yes?
But this accounts only for distance, not for direction.
No, this accounts for, I mean, you know, when I was plotting, let me just redraw this one.
You look at the trajectory over there. You want to compare it to a random walker, right?
Yeah, I mean, you don't know what the animal did to go from here to there. So he might have done this, might have done this, he might even have done that. But because you have a sampling rate. But I mean, the actual, when I do for you the one at the computer, you really take into account all the possible trajectories, all of them, and they have all sorts of shape. Now there are people who have, I mean, they actually tend to use this. Not many, few people, I can point to some of these papers. They are not rigorous, which means there is not a fundamental basis like this, which I'm trying to build, which what they do, they study versus, they choose a radius, and they slide it, along the trajectory, and then they try to interpret what they see sliding along the trajectories.
Yeah, this has been mainly done, or not mainly, but at least occasionally done in the context of the foraging, where there is a patch, because if you look on the graph how long it takes across the radius, and let's say in general it's here, then you see a drop, so the animal stayed more.
Correct.
And assuming that it has the same velocity, so
Correct.
it's been more towards, and this drop in this figure shows.
Correct.
But actually Roy over there in the corner is shy, and he has done some intensive work on this aspect. Maybe you want to tell him like.
Yeah. So I mean, what I'm claiming is that, I mean, now there are tools which have been developed, I mean, a different world, which is physics, which people may not know about, which gives you some, I mean, solid quantitative understanding. Now, of course, with this aspect of the shape has to be always there, so there are some approximation there, and it's something that people can exploit. And I'm trying to do that. So, I mean, now in particular, now you can ask the question. Unfortunately, I can't tell you yet what about the correlated random walk. How does it depend? Of course, the intuition is 1 over the capital T. But you know, if you give me a week, I'll give you the exact answer. Okay. So I just started a couple of weeks ago thinking about this. Okay. But this is.
You have a day.
Eh?
You have a day.
You have a day. So, but this, I mean, remember, yesterday I told you about using mean square displacement to characterize, if you want, the walker. This is another method. So you exploit first pass of time calculation to extract parameters of the walker. In this case, I just told you precisely this is about D, but eventually also about the capital T and V. And so which method is better? Well, remain tuned, whatever they say.
Stay tuned.
Stay tuned, okay. Okay. So clear, no? Hopefully. Now, someone was asking me about, so you start at the center and then you reach the target now. But of course, think about the other situation where you actually, here is the target, and you know that you start from some distance away. So you ask the reverse question, no? So now the target is, so the target, let's put crosses for targets. And now you are some distance away.
But then what's the difference between just one target?
Aha, it's a big difference. So now notice that I mean, just to tell you, well, it's, how should I tell you? Well, so first big difference is that here you have one initial condition and many targets.
Not from this situation.
Oh.
Just from one initial condition and one target.
Yeah.
The case you go before you get to the distance. It's the same as here, just the starting point is always distance from the target.
I mean, what is the same is that the distance is the same, but the dependence or the property that you expect from this process to that process is.
I'm not comparing these two processes. I'm comparing the process that you first showed. Only one target that you calculate in the time.
Oh, you mean if I do this? So what you're asking is that since you were seeing that I was drawing this, and then you say this one. You were saying that this, if I draw, I mean, I start from any of these. That's what you're saying, no? Because you're going to see a similar drawing, no?
No, but not these two.
Oh, okay. So
that's the case when you start from one.
okay, let's go back. So let me draw it so that we understand what you're asking. Yeah? So I have one starting point
One target.
and one target.
And what's the difference between this and
This one. Well, because here you know exactly what your initial position is. Here you don't.
But the initial position is not something very special, it's just in a special distance from the target.
Yeah, I mean, yeah. So, yeah,
That's
okay.
true for all the
Correct. I mean, the point is that the fundamental important characteristics is what is your distance from the target. That's true. That's true. But, you know, things are going to change here a lot.
just because you start from different sides of the target?
Because, you know, you have, you know, it's more of a computational thing. I mean, the scaling is always the same. So remember that this is where you start. Don't get confused. Okay, let me backtrack a second. I think I understand why you're asking this. Let me backtrack a second. So when you compute this mean first pass of time, there is an area where you're roaming, and there is a target, and there is an initial condition. There are three quantities. So there is an initial condition of the animal, x naught, let's call it. There is a position of the targets, let's call it capital X. So x naught, capital X, target. And then, if it's not infinite space, there is an area of where you're roaming, home range or a territory. So these are the three quantities. And then there is the statistics of the animal.
So there, in the case of the last case of the drone, the animal can't go to the other side of the circle. It can only go to the center.
No, that's right. So that's why I think you were asking me. So this is, you have an area which is the blackboard, which is A, and then you start here, and you want to know how much time it takes to get there.
But when you start there, it can also go to the...
Correct, because I mean the area is this. So okay, let me just, so then I think I'm going to help you understand. So as I said, there are three quantities here over which you expect the dependence. So if you want, this reduces to a sort of a distance, let me call it d, between original position and target position, as you would expect. And then there is the area over which you roam, the entire area available to you. Now, let me just add one more thing, is that if you have an unbounded space and you try to make this computation, so the animal is really in an unbounded space, and you try to ask, what is the quantity, what is the mean time, the mean first passes time to get to a target, which is now this situation. So there is a distance d now. Then you can ask that question. But if the animal is really in an unbounded space, what do you think is the answer? So there is no a. I mean, a is infinite. If you think about drawing trajectories, okay, there's going to be this and this and this. Then I'm going to draw one. I keep going this way, and then I get there.
But eventually you will get there. We had this discussion 2 days ago when we said that eventually within two-dimensional space you'll get to any given area, no?
Yeah, in an infinite time.
Yeah.
That's what I'm saying, it's useless.
But it will happen, eventually it will happen.
But yeah, I mean, it's useless. Think about it. If I tell you, okay, it will happen, but it's useless. In the sense, of course, the reality is that, you know, at least the Earth has a finite, a finite shape. But what I'm saying is that it becomes useless. So the more the animal is unbounded, the more these concepts that I'm telling you, they're not very useful. The reason being is because, I mean, I'm just telling you, theoretically, you're going to have a mean first pass time which is infinite. So it's not of great use. If you have a quantity which is infinite, then, you know, what are you going to understand? Oh, I see, it's becoming infinite. It keeps increasing. So you do another simulation, there is another result which is even larger, and then larger, and larger. So it becomes useless.
Yeah, but this is the mean and not the minimal. The minimal will not depend on the size A, only the average.
Correct. Yeah. Remember, these are, you know, again, this is average over trajectories. Eh? So if you want to have the support of some theoretical underpinning, then, I mean, it's inevitable. You have to rely on some average over trajectories, and in the context of open space, then it's not very useful. But of course, most of the animals, they have an area where they roam. Well, the nomadic one maybe not, but if you have a home range, then we should not worry. I just wanted to make, sorry, it just happens that it occurred to me that I wanted to tell you this. Okay, let's go back to what you were asking. So now you have this quantity. So what you are interested in determining, given this situation, what is the dependence on A, D? That's all you want, no? Because remember, you are calculating the mean first passage time, which is, we decided to make this symbol tau, and that will be a function of A and D. Since it's a mean, it will just be dependent on A and D. Now, I told you the first dependence, and then there is A over D. Yeah, sorry, I forgot to put the diffusion constant of the animal, so that there is a characteristic of how the animal moves. So it's A over D. And then what about the dependence on the distance? So there are corrective factors here, which are inside this function, which are log of D over the size of the target. Sorry, the other way around. It's A over, let's say A is the size of the target. Maybe you don't see. Let me just write it bigger. Size of target.
AND is the distance to where? So the target has a size of it.
No, this is, oh, it's the center, yeah.
Center.
So your initial position, and then here. These are results of a few years ago, so not mine, okay. But so it's an important dependence because it's very peculiar, and I really find out why it comes out to be like this. But okay, so this is a physics talk. But anyway, this is
the angle to the target. If you are close,
yeah. Then you have additional corrections. Then you have to, keep correcting and so on. So that becomes, the geometry as, similar to what he was asking now. As you start having a geometry, and then you can imagine that if you are close to a reflecting boundary here, and then your target is here, then of course, since you reflect, the chance of getting there is, so you are going to have a different value. So you have to keep track of this correction.
I meant that the ratio between A and D makes sense intuitively because it's like the angles that you see. Like if you try to see how much, what is the size of an object on your retina, it depends on the size.
Oh yeah, this is it. No, yeah, but I would just challenge you to tell me why it's a log.
Well, you just have to do the second derivative.
Okay, so anyway, okay, so I hope, so now you understand. So there is a dependence on these quantities. And so I hope it clarifies what you were asking. Okay, no, yeah, ask him again, yes.
Just to that question, I think, if in this example, the area is unbounded.
I assume that remember this.
It's there, but you can go anywhere. Then the answer is the same. It's infinity here and it's infinity here to reach the. Yeah. So this is it's right. There's no difference between the situation when it's unbounded.
Correct. In fact, notice that an area unbounded. You can see easily from here. It's. Again, this is good because it's ratio length scale, no? If you think about this one is becoming very tiny with respect to this. So essentially as if you're going in unbounded space, no? And so this is going to explode. So this, but it's a direct dependence, so there's a lot. So this becomes infinite. So even if, notice that even if the capital A is finite, but I make this smaller and smaller, becomes a point, it's infinite. As we were chatting, now even in finite space,
it's a point,
if it's a point, and think about intuitively, if I have to just throw random numbers and hit this, because it's a real number, no? I never hit that specific number, no? So if you want another way of thinking also, but if you make the size of this target smaller and smaller, with respect to the distance, then eventually it's going to take an infinite time.
This is if you don't have an area as well.
No, even if you have an area. Yeah, because again, a point in 2D has a coordinate x and y. These are real numbers.
No, but if the animal that is looking for the target has an area, then it will go on. So.
Well, you're thinking about, okay, biology, yes. Of course, eventually you will find it, no? But why is it going to find it? Because, there is a perception range, and the perception range, if you want, is this value of A. As soon as I'm away from a distance A from the target, even if it's a point, then of course I'm going to get it. So this is the reality. Now I'm just saying that if you actually were in a situation such that you make this perception range smaller and smaller, only if I really, just stumble across, on this object and I'll get it, so in principle it takes an infinite amount of time because you will never stumble. Of course the animal even has, it's not a point, the animal eats itself, it has, a size and so on, so this discussion is just, endless. But you understand?
This log is a characteristic of what? Or it's part of the function?
Yeah, it's if you want, yeah, it's here. Let me just write it more precisely. So it's proportional is A over D. So you have the right unit of time here. Area divided by this diffusion constant, distance squared divided by time. And then you have, A over D. writing only the minus in front, because so that with the, you know, the property of the log. So there is a minus here to get the right sign. So if you want, since it's a log has this property, you change the minus, you put d over a. No, it's the same thing. So that this becomes, I mean, positive infinitely. Yeah? Now geometry here is important. As you go to 3D, this function is not anymore a log and so on. So the geometry is quite important in defining the functional dependence. So still there is going to be a d over a dependence, but it's not log. All good? Yes?
There is no dependence on the topology of the area?
Yeah, there is a dependence. As I said, there are correction factors here. These are not exact correction, but these are all approximate. So these are nasty calculations to get to this point. So, and of course, as you know, I was answering to or, if you are in a situation that I was drawing here, you know, your initial condition also, if you are close to a boundary, since you have, I mean, you don't have many trajectory, you know, just give you two different situations, no? Let's suppose this is the area, where, and then you start here, and that's the target. Then, okay, you compute things. But notice if I put myself, so let's put the target. If I put myself here, just close to the boundary, then you know many of these trajectory that made me go this way here, now here I'm going to bounce off. So this is going to be, there's a difference. And this is the topology, because you're close to the boundary. So there is a difference. So these are correction factors. These are the main characteristics is this. Or if you want, the even more important is this. If the target is sufficiently large, no?
Topology of the target also.
And then yeah, the topology. But these are corrective factors. So they have less importance as you keep adding them. All clear? So what I want to tell you now is, so should we have a break, or we can keep on until I exhaust you? Are you okay if I continue? No? Okay, short break. Okay. 10 minutes, yeah, whatever.